Imagine dropping a camera through a crack in the Antarctic ice. At first, it looks empty. Black water, drifting particles, and a seafloor frozen in silence. Then something moves. A sea spider steps from behind a sponge, except its legs stretch wider than you expect any spider-like animal to grow. Farther out, a squid built like a living torpedo disappears into the darkness. In most places on Earth, cold and scarce food should make life smaller. Around Antarctica, some animals seem to have ignored that rule completely. This is called polar gigantism. In several groups of marine invertebrates, species living in polar water can reach much larger sizes than relatives in warmer seas. But the real story is more complicated than cold water makes everything giant. Antarctica does not turn every animal into a monster. Instead, its ocean creates a rare combination of conditions where certain cold-blooded animals can push body size much further than we would expect. And the most famous creature in this frozen world is almost impossible to study alive. The colossal squid lives in the deep southern ocean around Antarctica. It is not simply a longer giant squid. Giant squid may be longer because of their stretched tentacles, but the colossal squid is heavier, thicker, and more muscular. One famous specimen weighed about 495 kilograms. Its arms carry swiveling hooks, its beak is enormous, and its eyes are among the largest known in the animal kingdom. This is not a fragile ghost drifting through the deep. It is a powerful predator designed for darkness. Much of what scientists know about colossal squid comes from rare specimens, fishing vessels, and beaks found inside sperm whales. An animal weighing hundreds of kilograms can live in our ocean and still remain almost invisible. But why become so large? One part of the answer may be oxygen. Cold seawater can hold more dissolved oxygen than warm seawater. That matters because every animal has to deliver oxygen to its tissues, and as bodies become larger, that job becomes harder. In some marine invertebrates, researchers have found a link between oxygen availability and maximum body size. Antarctic water is cold and oxygen-rich, so one barrier that can restrict size may be weaker here. But oxygen is not a magic growth potion. If it were, every Antarctic animal would be enormous. They are not. The better way to understand polar gigantism is to look at the entire energy budget. For many ectotherms, or cold-blooded animals, low temperature slows metabolism. Their bodies do not burn fuel constantly to maintain a warm internal temperature. Movement can be slower. Growth can take longer, and in a stable environment where temperatures do not change dramatically, there may be less pressure to live fast and reproduce fast. That brings us to one of Antarctica's strangest animals, the sea spider. Despite the name, sea spiders are not true spiders. They are pycnogonids, and they look like evolution started with legs and nearly forgot the body. In some species, the central body is so narrow that parts of the digestive and reproductive systems extend into the legs. And in Antarctica, some of them become huge. Their biology makes the oxygen question even stranger because sea spiders do not breathe with lungs. Oxygen moves across their body surface, especially through those long legs. Studies of Antarctic sea spiders suggest oxygen matters, but the rule is not simple. Body shape, activity, circulation, and species-specific adaptations all play a role. Still, the visual is unforgettable. A delicate, spider-like creature from a normal seafloor can become something that looks almost alien in Antarctic water, and sea spiders are not alone. Antarctica is known for unusually large amphipods, sponges, worms, and other bottom-dwelling invertebrates. Many grow slowly in near-freezing water. Food may arrive in seasonal bursts, so instead of racing through life, many species are adapted to wait. That slow pace changes what survival looks like. In warm oceans, metabolism is faster. Predators may be more active. Competition can be intense. A small animal can grow quickly, reproduce quickly, and disappear quickly. In Antarctic water, the clock runs differently. Growth may be painfully slow, but once an animal reaches a large size, that body can store energy and become harder for smaller predators to attack. So becoming giant is not always about becoming a better hunter. Sometimes it is simply another way to survive a world where everything happens slowly, and this is where the mystery gets deeper, because the deep sea can produce gigantism too. Deep-sea gigantism describes the unusually large size of some animals living far below the surface. Food can be unpredictable, pressure is enormous, temperatures are low, and some animals may benefit from storing energy or moving farther between meals. The colossal squid lives where these worlds overlap. Deep water and polar water. Its size probably reflects a mix of ancestry, prey, predators, temperature, oxygen, and deep sea life. Nature rarely gives us one clean reason, and every time you think you understand Antarctica's rule, another animal breaks it. Take Antarctic fish. Some ice fish have adaptations so bizarre that certain species lack hemoglobin, the red oxygen-carrying pigment almost every vertebrate depends on. They survive partly because their cold environment contains plenty of dissolved oxygen and because their circulatory systems are highly specialized. Yet these fish are not simply giant tropical fish. Some Antarctic species remain small, others occupy narrow ecological niches. The same environment that allows gigantism in one lineage can reward the opposite strategy in another, so polar gigantism is not a universal law. It is an evolutionary opportunity, and warm-blooded animals follow another set of rules entirely. A polar bear is huge, and an emperor penguin dwarfs many warm-climate birds, but their size works differently. Mammals and birds generate body heat, and larger bodies lose heat more slowly because they have less surface area relative to volume. This general pattern is connected to Bergmann's rule. Within many groups of warm-blooded animals, colder climates are associated with larger body size. Bigger bodies conserve heat better, but being large comes with a bill. A polar bear must fuel that body. A seal must keep producing heat. A penguin has to find enough food to survive and reproduce. For warm-blooded animals, body size is always a negotiation between heat conservation and the cost of feeding the furnace. Cold-blooded marine animals play a different game. They can let the environment control much of their body temperature, making the Southern Ocean an extraordinary evolutionary laboratory. And there is another reason Antarctic animals can feel like relics from another planet: isolation. Powerful currents help isolate the Southern Ocean from warmer seas. Over millions of years, many Antarctic species became tuned to a narrow range of extreme cold. That specialization created extraordinary animals, and it also created a weakness. Warm the water, and several things can happen at once. An animal's metabolism may speed up, meaning it needs more oxygen. At the same time, warmer seawater generally holds less dissolved oxygen. Demand rises while supply falls. For a giant animal, that squeeze can be dangerous. This is why scientists are studying whether large polar invertebrates may be especially vulnerable as oceans warm and oxygen levels decline. Experiments with Antarctic amphipods suggest larger species can be more sensitive to reduced oxygen, although the response differs between species. Evolution built these animals for a cold, oxygen-rich world. Change that world quickly enough and some of their greatest advantages may become weaknesses. Think about how strange that is. For millions of years, cold water helped create conditions where some animals could become enormous. Slow metabolism rewarded patience. Stable temperatures allowed extreme specialization. Isolation gave evolution time to produce creatures found almost nowhere else. Then the ocean begins to warm. The same giant body now demands more oxygen. The same slow life cycle that worked in a stable ecosystem can make rapid change harder to survive. The same specialization that made an animal perfect for Antarctica can trap it there. And this is what makes polar gigantism more than a collection of giant monster facts. These animals are experiments that have been running for millions of years. A colossal squid is not terrifying because it is waiting beneath the ice to hunt humans. There are no confirmed records of one attacking a person. It is terrifying because something so massive can exist almost completely outside our experience, hidden in a place we have barely explored. A giant sea spider is not fascinating because it resembles a horror movie creature. It is fascinating because its body shows how differently life can solve the basic problems of breathing, feeding, and surviving. Here, a spider-like animal can take in oxygen through its legs. A squid can weigh nearly half a ton. A fish can survive in seawater colder than the freezing point of fresh water. Animals can grow at a pace that would seem impossibly slow in warmer seas. Antarctica does not break the rules of evolution. It reveals how flexible those rules really are. So if you imagine the ocean beneath Antarctic ice as empty, remember that the cold is not a lifeless void. It is a filter. Most species cannot tolerate it, but the ones that can have had millions of years to become something extraordinary. Some became slow, some became bizarre, and some became giants. The real mystery is not why life survived at the edge of freezing. It is how far evolution was able to push life once it got there.